Hello, and welcome to ImageJ Fiji Image Processing Basics. My name is Dominic Alibi, and this course was put together with my colleague, Dr. Stephen Cross. Both Stephen and I work in the Wilson Bioimaging Facility at the University of Bristol. Our website's in the bottom right-hand corner of every slide, and on the website there's lots of useful information about the facility, the equipment we've got, and various image processing information as well. So just start off with a brief overview of the course. So this course itself is really designed as an entry-level course. No prior knowledge is assumed at all. We don't even assume you know what ImageJ is or have ever seen it before. So if you do have any experience of ImageJ or general image processing, parts of this course may seem a bit slow. We ask you to bear with us. It will pick up, I promise. But if you just can't wait to get started, the course is designed to be self-paced, so feel free to skip ahead, we won't be offended. Structure of this course, is broadly speaking, is made of two halves. First section, I'll give a brief introduction to image acquisition and an overview of image processing techniques, and hopefully this will be done in a very general way, sort of presenting you with the ideas so you can use them not just in ImageJ, but hopefully in any other image processing piece of software that you'll be using. And then Stephen will go through a dedicated section, which is really the hands-on part of image processing with ImageJ, putting all the kind of general theory from my section into practice, hopefully, or it's the plan anyway. As I said, the course is self-paced, and there are exercises for each section, so you can work at your own pace through the exercises. All the slides and exercise sheets and the example data is available to download from our GitHub repo, and the link should be somewhere in the show notes below. Also on this slide, we've just got a few useful websites for further reading. There's a Nikon Microscopy U website, the SVI Huygens website, which has a lot of really good detailed optical diagrams and descriptions of microscopes. There's the Zeiss and the Leica. You can't have one without the other. And probably the most useful website is the bottom one, which is the ImageJ NIH user guide. So that is really the complete sort of Bible of ImageJ that we would recommend you probably download and have a look through before sort of really cracking on with your own image processing. So for the course itself, we'll be doing some processing on some example data. So it's this nuclear kind of image that's shown on the left here. And what we'll be doing is we'll be doing some importing of that data, pre-processing of it just to kind of get it into a format that's easier to process. Then we'll move on to doing some image processing and segmentation. So in this case, we're just kind of showing how we kind of threshold and pick a threshold. Then we'll do some object identification and finally some quantification. So these example images here are the actual data you'll be using, and hopefully you'll go from a 3D data set acquired on one of our confocals in the facility through each step by step, building it all the way up to automatically identify each of these cell nuclei, and then measure the area and various other parameters of each of those nuclei individually and automatically. So where do we start? Well, we've got to start, unfortunately, right at the beginning, because this is an introductory course, with the experimental steps. So if you want to get to good quantifiable, good quality data, each of these steps builds on the previous one. So you've got to start all the way down at the bottom of the ladder, all the way down at sample prep. So you've got to get good sample prep. What do I mean by this? Well, I mean, you've got to consider how you're preparing your sample, so using the appropriate mounting medium. First of all, I suppose you've got to consider using the right cover slips. So number 1.5 cover slips for high microscopy, high tolerance cover slips preferably will give you the best quality images, and you've got to clean them first, so don't just use them straight out of the pack. Take them and maybe acid wash them ideally. If not, just ethanol, 100% ethanol cleaning, and store them in ethanol before using. Once you've got your sample prepped correctly, then you've got to set the acquisition up in a reasonable manner. So this is things like using an appropriate laser power so you don't saturate your sample or bleach your sample, or if you're doing live cell imaging, introduce any imaging artifacts, and consequently you've also got to set it up so that you get a good signal to noise in your image, so you can actually see what your signal is clearly above any background noise, depending on which sort of detector you're using. Then we get into more of the image processing steps. So the first step really is to adjust the visualization settings, so adjusting things like brightness and contrast and things like that. And if you get that right, you might look as excited as this guy here. He's obviously seen something he's pretty excited about. And then moving on from there, we move into more segmentation based routines. So this is kind of identifying what objects are, separating foreground from background. And finally, once you've got all of those steps done, you can then start pulling out numbers. So if any of these steps you get kind of drastically wrong, it's going to affect everything subsequently in the kind of pipeline here. So if you have crap images basically going into your quantification, you're going to get crap data coming out. So when you arrive at the microscope, one of the first decisions you'll have to make is which objective to use. So every objective has got two main numbers you're going to be concerned with. One is the magnification and one is the numerical aperture. So these two are shown on this objective just here. Now the magnification is pretty obvious what that means. The bigger the number, the bigger your resultant image is going to be. So the more zoomed in effectively you are. The numerical aperture is a little bit more abstract. In sort of conceptual terms, it is the angular acceptance of the objective itself. So in your sample, small things will be emitting at what's called high spatial frequencies. And high spatial frequencies correspond to high angles. So if you have a high angular acceptance or a high numerical aperture, this light emitted from the small objects can actually be collected by your lens. If you have a low numerical aperture lens, so a low angular acceptance, the high angle light is not collected by the lens and it doesn't form any part of the image. So the resolution itself is defined as the minimum distance between 2 points, which allows them to be distinguished as individual objects. And it is the NA of the objective which determines the resolution, not the magnification. So if we look at this equation here for the lateral resolution, the Rayleigh criterion for lateral resolution shows 0.61 times the emission wavelength over the numerical aperture. So as your numerical aperture gets higher, your resolution will improve, and your resolution in Z is always about 2 to 3 times worse than your resolution in XY. As already discussed, the magnification will determine how big your object is in the resultant image. Now, the magnification and numerical aperture, generally speaking, will scale together. So normally, if you've got a low magnification, the numerical aperture is really quite low as well. So 10 times normally, you don't really get above 0.5 NA. 20s, you're talking about 0.5 up to about 0.9, generally speaking. 40s from about here, about 0.6 up to about 1.3-ish, 1.2, 1.3. And then 60 and 100, you can get up to about 1.4, 1.45 NA. So remember, the numerical aperture is the resolution defining element. As the NA gets higher, your potential resolution will increase. Magnification plays a much bigger and more important role in camera-based systems, so wide field, anything that uses a camera. You have to also take into account sampling, and so the magnification plays a much bigger role in your choice of objective when using a wide field system. If you're using a confocal, I would use, and you want to get the highest resolution possible, for example, then you want to look for basically just the highest numerical aperture. In this case here, I've highlighted two potential objectives you're going to be potentially using, a 60 and 100 times. They're both 1.4 NA, so we know the NA is shows you what resolution you can potentially achieve. So they should both give you the same resolution, or maximum resolution. What's interesting to note is as you go to higher magnification, your brightness, your image brightness, is defined by these equations over here for transmitted light imaging and epifluorescence imaging. they'll scale with in the denominator with the magnification. So as your magnification goes up, you get less and less light through. So for confocal imaging, if you want the highest resolution possible, you pick the highest numerical aperture and you pick the lowest magnification. As I mentioned, for wide field systems where you have a fixed pixel width in your camera, or fixed pixel size rather, in your camera, you have to take into account magnification for sampling. And I'll be going through sampling in a few slides to explain what that means. So moving on to bit depth and generally what digital images are. So we have an image here, just a sample image. We just take an area of that and we move in and zoom in more and more and more, a bit like CSI. Eventually, we get one more, we can see all of the individual pixels there. So each of these pixels is a different color, different level of grey. And that's called a grayscale image. So every pixel has a particular sort of color associated with it, and underlying those colors are a whole host of numbers. So you can see sort of these areas down here where we have lighter, sort of brighter signal corresponding to about 40, 45, 50 on this scale. And right up here we've got some dark pixels, very dark pixels. These are about 8 or 9, 10 maybe intensity levels or intensity grey levels. So what determines the range of numbers we can use? And this is the bit depth. So for a bit depth of 1 bit, you have 2 to the 1 possible values, so 0 and 1 normally. So that's called a binary image. This is a special case that we'll be going through a bit more detail later on. Other bit depths can be 8-bit. This is standard for most microscopy imaging, so 2 to the power 8, so 0 to 255 or 256 possible different grey values. 12-bit and 16-bit are other bit depths that are available. So for example, if you're wanting to do quite fine segmentation, potentially increasing the bit depth does help in some segmentation modes, gives you slightly better separation between background and foreground at a cost of much, much, much bigger file sizes. A slightly special case is RGB images. So RGB images or color images, these are normally images obtained if you're doing generally kind of sort of tissue sectioning, so H&E staining, brain sections, those sorts of things, and you want a color camera. So RGB images rather are made up of 3 8-bit images, one in the red channel, one in the green channel, one in the blue channel, and you merge them all together and you'll get a color image. So each pixel in this case contains 3 values. For analysis, this can be split into the constituent channels or kept as an RGB image, depending on which sort of analysis you are looking to perform. So if you're looking to use the color to segment out different parts of your image, then keeping it as a color image can be useful. Occasionally, it's easier to just split it into 3 8-bit images and do standard intensity-based segmentation on individual channels. You might get better contrast just using the red channel, or better contrast just using the blue channel, and you don't need to worry about the other 2 channels. So as I mentioned, we'll discuss what sampling in an image is. So if you imagine light as a wave, which it can be thought of, you're going from an analog system there, so you're going from light as a wave, collecting through your objective and forming a digital image. As we saw with that zoomed in image, every pixel has a discrete intensity value associated with it. So you have to go from an analog system to a digital system. And to do that, you need to sample the image. So if we take 3 example sine waves, all identical sine waves, and we have 3 different levels of sampling. We've got oversampled here, so to reconstruct this nice smooth analog signal, we can make a whole load of points all the way along it, loads and loads and loads of measurements, and then when we reconstruct the analog signal, we'll get a very high fidelity reconstruction of that. So this is not necessarily bad, but it will take quite a lot longer to make all these measurements. And in terms of imaging, will probably cause quite a lot of photo damage to the sample. If it's a dynamic sample, if it's a live sample, the scanning time will be massively increased. We'll probably lose some information from the dynamics. On the other end of the scale, we could be just say, okay, we'll make 3 measurements, here, here, and here. And then we'll try and reconstruct that. And if we reconstruct that, we'll just get a straight line. So this will be losing all of this information. And this is undersampled, so it's called aliasing. The best case scenario is that kind of Goldilocks region somewhere in between. And this is known as Nyquist sampled. And so Nyquist sampled is essentially the minimum sampling rate to capture the signal. So for our really simple sine wave case, we have 5 points we can measure. One at the 0 cross, then the maximum 0 cross, minimum 0 cross again. If you have those 5 points, you can then, with a pretty good fidelity or high fidelity, reconstruct the underlying analog signal. So in terms of imaging, what does this look like? We take our nice convolare slide again. If you have a massively oversampled image and the Nyquist sampled image, there's not too much difference that you could see between those. Obviously, no one would ever take an image this badly undersampled unless they had a very good reason to. Undersampling gives you massive pixels and a completely loss of some of the finer structure that you can see in here. For example, these whole nice bits here are completely merged into the overlying structure. This becomes a bit more apparent if you take that line that was plotted there, and you can see the Nyquist sampled, you can quite nicely see these 2 peaks. The undersampled is you're kind of losing information. The width of these lines is massively broadened. And even in the oversampled version, you're kind of introducing a lot more noise. And that's just because your pixel size is considerably smaller. So you're going beyond what is necessary. And therefore, you're just introducing noise. You're reducing your signal per pixel, and therefore your signal to noise will drop. So generally, what does all that mean in terms of rules of thumb? So we have smaller features in the image correspond to high spatial frequencies. So when you're setting your pixel size in confocal, it's important to sample the image appropriately to avoid aliasing in the image. And as a rule of thumb, work out your resolution from the Rayleigh criterion, and then divide it by about 2.5-ish, 2 to 3. That will give you an appropriate pixel size. This isn't always possible, like I mentioned, due to photo bleaching. Sometimes you're more interested in temporal dynamics, for example, less interested in spatial measurements. In that case, you have to take into account what you're really trying to measure, and also you need to take into account the size of the object, or the expected size of the object that you're looking to measure. If you're looking to measure a whole cell and its location within a tissue, you don't need Nyquist sampling working at full resolution. If you are looking at mitochondria within a cell, you're going to have to use a high power lens, and you're going to have to be working at the Nyquist rate to fully make use of the objective that you're using. So we need to be roughly aware of the smallest feature you're in. In terms of calculating the Nyquist rate and Nyquist sampling, then I'll direct you to these websites by the SVI guys who make Huygens deconvolution software. Some information on what the Nyquist rate actually is, how it's calculated, and then a really handy Nyquist calculator. They've even got it as an app if you want, so you can download the app and calculate your Nyquist rates wherever you are, anywhere in the world. Lovely. So that's basically what I wanted to go over in terms of setting up the microscope. So hopefully by using those techniques, you can have a better understanding of what parameters are really important to get high quality images. The next brief section is just going through some basics of image processing in a really kind of a bit more of a hand-wavy, generalized way. Stephen's then going to go through in a very specific way in terms of Fiji ImageJ. So there's 2 broad reasons you would want to do image processing. So generally to improve the signal to noise of the image. This is kind of what I would call sort of pre-processing of the image. So background subtraction, filtering, the image will get a bit nicer, nicer to look at. From there, you can then move on to doing things like segmentation and measuring features within the image. So measuring things like size or shape. So shape parameters, for example, circularity, how circular each object is. Intensity or ratio of those intensities per channel, tracking objects over time, measuring changes over time, or changes after stimulation, for example. So a quick word on file types before we start. Generally, TIFF is a really good choice if you have to force by ImageJ or any other software program to save your image as a particular type. Generally, we would suggest just stick with TIFF format. They provide lossless storage. There's header tags for metadata. So metadata is all of the information that comes from the microscope and is saved with your image. So even though you don't see it, all of the images will have a whole load of metadata saved with them. So which objective you used, which laser power you used, what detection bands you set, a whole load of useful things that enable you to repeat your image if you need to, or remind yourself of how you actually set up your experiment. They're also multi-page compatible, so stacks and multicolor tile scanning, etc. So you can have one file that encompasses your whole Z stack rather than having a whole series of individual files for Z plane 1, Z plane 2, Z plane 3, etc. Proprietary formats are the most complete. For example, most of our microscopes are Leica microscopes, so they save in a .lif file. They will provide lossless storage. They should contain all the metadata, not always, but they should really contain all the metadata. However, they're proprietary, so they require readers for viewing outside of Leica software. Thankfully, Fiji comes preloaded with Bioformats Reader, which is a reader that is able to read in a whole host of different microscopy image formats. So Leica formats, Zeiss formats, Olympus formats, astronomy formats, a whole load of other stuff as well. So Stephen will go through how to actually use the Bioformats Reader. We would always recommend keeping a copy of the raw data in proprietary format and then do all your processing and save all your processing in TIFF format, but always keep the raw data, the LIF file, for backup. PNG is very good for data transfer, sort of transfer display type things, so it provides lossless compression. It's a color image, RGB only, but you lose all the metadata. So for posters, you can reproduce quite high quality images with PNG. And JPEG, I've got just don't. I'm kind of reverting to thinking that's a bit harsh now. The reason I put just don't is you can see over here you've got a TIFF version of the image and a JPEG version of the image. And so you can kind of see on here a little bit of artifacts introduced if I change that to a constrained intensity scale. The TIFF image here, you still have all the nice sort of noise speckle that you can see. So this is actually sort of what a real image should look like. And the JPEG, you can see all the artifacts introduced from the compression. So the way the JPEG works is it just says, okay, here we've got an area that looks pretty similar intensity, so we're just going to block it out as one color. And that's the way that it can achieve much smaller file sizes. The downside is, if I flick back, that you lose quite a bit of detail, so things just get a bit more smoothed out. So for quantification, just don't use JPEG. But for display, for sending images, quick presentations in the office, etc., JPEG is fine, I would say, but don't do any quantification on a JPEG. In terms of image types, microscopes now go anywhere from 2D up to about 7 dimensions. ImageJ itself, the Bioformats Reader in ImageJ, can handle up to 5 dimensions. This is into the realms of what's called hyperstacking. So we can have XY for 2D, or even just X and time. 3D, XYZ or XYT, XY and different channels. And then hyperstacking is when you start mixing all these different parameters together. So you can have XYZ, so 3D data sets in terms of 3 spatial dimensions and time, or 3 spatial dimensions and time and 2 different colors, and the list sort of goes on. Now, one of the first or main things you're going to have to do in image processing is to threshold your image. And to do that, it will use the histogram of the image. So the histogram of the image will show the probability density function of the intensity values, with the range of intensity values determined by the bit depth of the image. So essentially you can go through that little grid of all the intensities in a particular image that we showed in the bit depth slide, and you just put them into a histogram. So add up the frequency of each intensity, and you might get something that looks a little bit like this. And then when you form a threshold, you separate out foreground, so the objects of interest, from the background. So in this case, you've got a whole load of peak of pixels here. This is probably your background, sort of slightly noisy background. Then you've got the secondary peak here. So this is probably reasonable to say, okay, this might be where my objects are. So a reasonable threshold is somewhere in between. So this sort of dip in between. So you could do that manually. ImageJ allows you to do that manually. You can kind of tweak that for each image, get the adequate thresholding, but that inherently introduces bias. So there are various algorithms available. There's a whole load of algorithms available in image processing. In Fiji, there's 16 that are available to automatically determine where this threshold is. And they all have underlying different assumptions to make, depending on sort of assuming what noise and what sort of type of imaging you've performed. So within Fiji, the default one is what's called the Otsu. This is normally a pretty good choice. There's the Lee also and the percentile. These normally give pretty good results. They'll all be different results. They all will look slightly differently. In a way, it doesn't really matter which one you pick. You'll just need to make a note of which one you picked so you can actually report it in any paper you publish, because repeating someone's image analysis when they haven't actually told you how they've done the thresholding is quite annoying. So just make sure you pick one. They've all been published before, note it down, and then report it when you publish your paper. From thresholding, once you've made that decision of where the foreground is and where the background is, you get what's called a binary image. So this is what we discussed earlier, a special case made up of zeros and ones. So 0 for background and 1 for an object, or 0 and 255 as normally is done in ImageJ. So the threshold value is calculated from the histogram, and it determines the cutoff intensity. So for this image here, we get this much. This is what a real histogram of an image will look like. You have a really high background peak, and that's just because most of the pixels, when you look at it, are actually background. They're kind of black, or this kind of fuzzy noise. So this is what all this big peak is. All of these really bright bits are really this kind of small hump here. So the threshold for this, when you use the automatic Otsu threshold, comes out to be 23. So that shows just about here. And so anything that is 23 or above just gets coded as a value of 1, and anything that's below a value of 23 just gets coded as a 0. So you get this binary image, and this can be used as a mask, so you can kind of segment out areas of your image that are useful signal, and you can ignore all of the background. The final thing we're going to go through is filtering images using spatial filters. So spatial filters are image operations where each pixel is changed by a function of the intensities of the pixels in the local neighborhood. So this local neighborhood can be picked by you to be as big or as small as you want. Typically you're looking at sort of 3x3, 5x5, 7x7 sort of neighborhood, that kind of range. So for example, a mean filter in a 3x3 neighborhood for one particular pixel will look like this. You have your central pixel. This is the one that's going to be calculated for the mean, and then the mean values, or the individual values that will make up the mean, will come from these 8 pixels and the center. So you add the 8 pixels and the central pixel together, divide by 9 in a new image in the corresponding position. This pixel will be the mean of this 9 pixels, and then you raster scan this, what's called an image kernel, 1 pixel to the right, and you repeat. So we can have a look at that happen now. So you calculate that pixel, you move your kernel along 1, you calculate the pixel again for a new mean, you move it along again, calculate the next mean value, move it along again, and then calculate the final mean value. And then this will continue again and again and again, down one line, back the way, down one line, back the way again. So you can go from, in this case using a mean filter, having a nice image, but maybe a little bit noisy, and you can go and you can kind of smooth out all of that kind of intensity variation. Some examples of some other filters you can use. So this is a no filter image. Gaussian filter and a median filter are the two that I would say would be most heavily used. They're both quite nice noise suppressing filters. The difference would be really, you can kind of just about see it in this image. The median filter is what's called an edge preserving filter. So the difference, sort of the edge between the background and your signal remains quite sharp when you use this filter. The Gaussian is non-edge preserving, so the signal will just sort of blur slightly into the background. Choosing between these two we'll go through in much more detail in the hands-on part of the course. There's not much to choose, but it will really depend on what sort of object you're looking at and what you're really trying to achieve. And finally, one thing to throw into the mix is the Sobol edge detection can also be quite used. So this will be looking at the variance and how that changes across. So when you go from background to signal, you get a very high variance. You get a very big response from your filter. As you're going through the main sort of body of your sample here, there's not much change in the intensity, so you get a low response. And then as you go back from signal back to background, you again get this high response. So you can pick out edges quite nicely. This works quite well in images like this, where you have really good signal to noise, signal to background. Generally, when you put sort of live cells, this kind of thing falls down. There's a lot more detail in a cell than you would really realize. So you pick out all kinds of edges, but it can be useful to try. Well, that brings us to the end of this first part of ImageJ Fiji image processing basics. I hope it was at least vaguely useful. The next part is going to be taken over by Stephen Cross, who's going to go through how to implement some of the things we've been through in this first part practically within Fiji. Stephen and I are always available via email, or our contact details are found on the website in the bottom right of this slide, so anything doesn't make sense, you want clarification, feel free to email us. Thank you very much for sticking with us to the end of the course, this first part anyway. Hopefully you enjoy the second part.